Hello guys, welcome back again to my channel Gamma Digamma. Today we're going to be doing differentiability. In the last video we did continuity. So, I think both of them are good topics to be done one after the other. So this is the stuff I'll be covering in this video. Firstly, I'll be talking about why we need derivatives in the first place. Why discuss about them. Then I'll be talking about the mathematical definition of differentiability, like we did for limits, with the LHL and the RHL. And then I'll be doing some examples where they need us to analyze the differentiability of certain functions at a given point. Just like we did for limits. I mean, these chapters are connected, so it will be really helpful if you watch my previous videos of continuity. And then by the end of the video, I'll give you a brief idea about what the first principle method of calculating derivatives is. And I'll do, examples of finding derivatives by the first principle method in a separate video. So let's get into it, guys. Okay, say you have this nice linear function and you need to find the slope of this thing. So what you do essentially is you have 2 points, say y2 and y1, and their respective x values, say x2 and x1 respectively. What you do is you do y2 minus y1 all over x2 minus x1, or symbolically put delta y, the change in y, over the change in x, and whatever slope value you get remains the same for this line. Hope you know that. But what if we have a curved graph? Like instead of a line we have a curved function, an irregularity if you will. Okay, say you have a weird line like this, and for some reason, maybe you're just bored on one day and you're just fooling around and you want to find the slope of this line. I mean, even if you don't get this idea at first, many years ago Newton and Leibniz did. These are the fathers of calculus as it is. So yeah, they had this weird idea of trying to find the slope of this line. But the problem is you need 2 points for calculating the slope. I mean, you needed a y1 and a y2 here, and the corresponding x2 and an x1 here. So you need 2 points to find the slope. And unlike with this line, the slope is constantly changing, right? Because it's no more a straight line where the slope remains same. It's changing. So we need to be more specific. Now we can find the slope at a given point. That would make sense than the general slope, because you can't do that. You need to be more specific now. Say you need to find the slope at this point A. But the problem, as I stated earlier, is that you need 2 points for the slope. So what do? You can only find the slope at this point A. So you take a very small step, say h. So like this new x value is a plus h, and this corresponding function value is f of a plus h. So now slope at a becomes f of a plus h minus f of a all over a plus h minus a, which is just h. But the problem is if h is large, then the function isn't exactly a straight line over this small interval. It might curve even in that small gap. If it's a really unruly function, it might curve more, and the value of the slope would be a very bad approximation of the value of the slope at a, or how fast the function is changing at a. So we need a point which is very very close to a, but not a, because this would be undefined. This fraction would be undefined if h was 0. So we need it very close to 0 but not to 0. And I hope that rings bells, because we did limits last time. So we need the limit as h approaches 0. So h is very close to 0 but not 0. And in that very small interval, we can assume that the function acts like a line. The function becomes linear over that small interval, and this is a very reasonable assumption because h is tending to 0, and limits are the best assumptions. It's all about assumptions, and limits are the best mathematical assumptions we have at this point of time. I hope that shows you why derivatives are actually useful, and why we need to describe a quantity such as that. Now, yeah, you can write the slope at a as f dash of a, or the more famous notation f of x dfx by dx at x equals a. I'll elaborate more on this later. Well, we write the small d's because in the initial slope formula we had the deltas, delta y by delta x, and delta is just say d. But then over here we had the deltas becoming really really small, so we had the limit as delta x approached 0, right? So this delta became small, and we write this as a small d by a convention. Anyways, this notation will be helpful in later videos. Now, if you've been really attentive and have really understood my past videos of continuity and limits, then you might ask the question, I mean, this limit as h approaches 0 can go two ways, right? I mean, it's not necessary that we always need to have points which are we need to have a point that is only slightly greater than a. You can also have a point which is slightly less than a, say a minus h. And you can use these 2 points again like we did previously, to find the slope at a. So this choice, this option to select how this limit can be taken, introduces us to the concept of the left hand derivative and the right hand derivative. Now what we've taken here is the right hand derivative. This is quite analogous to the left hand limit and the right hand limit. So say for the slope at a, say f dash of a, the right hand derivative is what we've written above. So limit as h approaches 0 of f of a plus h minus f of a all over h. This is the right hand derivative, and the left hand derivative is when you take a small step less than a. So on the left side, so say f dash of a becomes the limit as h approaches 0 of f of a minus f of a minus h all over h. So the greater point is always first, because a minus h is naturally less than a. So yeah, and basically the condition for differentiability, I mean a function is differentiable at a given point, or whose slope exists at a given point, or you can say that it has a derivative at a given point, is when its left hand derivative equals its right hand derivative. Just like we had the condition for continuity, except there is no value of the function at that point. So it's just this one condition, one grand condition. And now we're going to be doing some examples where we're going to examine whether the functions are differentiable at a given point, or they have, put in other words, whether their slope exists at a given point, or how fast they are growing with respect to x at a given point. Now before we go on, I would like to state that even if a function is continuous, it's not always differentiable. Just because you prove that, from learning from the last video, that a function is continuous at a given point, it's not necessary that it's differentiable at the same point. Now, as you know, say we have the function, the absolute value of x, or I can write this in a piecewise form for you. So minus x less than equal to 0, and positive x for x greater than 0. Now you know that it's continuous at 0, right? Because we definitely have a value at 0. It's 0. And you can calculate the left hand limit and the right hand limit for it. Just to prove it. I'll probably leave that as an exercise to you. But the problem is, it's not differentiable at x is equal to 0. So I'll show you how, mathematically, that it's not differentiable, although it's continuous. So first off, let me calculate the left hand derivative at 0. LHD at x is equal to 0. So you have the limit as h approaches 0. So we need the function at a. So f of 0 minus h all over h, right? F of 0 is just 0 with this. So the limit as h approaches 0, 0 minus h, so it's negative negative 0 minus h. All over h. Now these negatives cancel out. All you have a negative h by h. Limit as h approaches 0 of negative h by h, which results in minus 1. Now we know that our LHD is minus 1. Let's look at the RHD, right hand derivative. RHD at x is equal to 0. Well, that's just the limit as h approaches 0 of f of 0 plus h minus f of 0 all over h. The limit as h approaches 0, 0 plus h is just 0 plus h, f of 0 is 0 all over h. This is just the limit as h approaches 0 of h by h, results in a 1. So the RHD is 1, and both of them are not equal, so they do not satisfy the condition of differentiability at a point. So the absolute value function is not differentiable at x is equal to 0, although it is continuous at x is equal to 0. I mean, I can probably draw its graph here. Yeah, let me do that. To give you a graphical intuition. Yeah, so you have absolute value function, which is like this. Now RHD is basically, say this is 0, right? So RHD is over here, 0 plus h, this point. Okay, so if you take 0 and a point at a very small distance from 0, now the slope between them is going to be positive, right? Because the graph is rising linearly on the positive side. So the plus 1 makes sense. But if you take a point which is slightly less than 0 and use it to calculate the slope, 0 minus h, you'll have negative 1, because on the negative side the slope is negative, so the graph is decreasing, right? Because of this discrepancy on both the right hand and the left hand side, that the derivative at this point is undefined. So we can set it as a general observation that whenever you have these spiky functions, something like this, then the derivatives or the slopes at these x values, these x value of peaks, is undefined, because on this side on the left side, in this case it's positive, here it's negative, and there's a disagreement, again positive negative disagreement, here negative positive, again disagreement. And this is when you have function with these pointy peaks. That's when, although they may be continuous, they are not always differentiable at every point. Please note that. So let's do an example. The f of x, again piecewise, is x squared times the sine of 1 by x when x is not equal to 0 and 0 otherwise. Yeah, so you might have guessed, if you saw my limit video, that when the LHD and the RHD, when the LHL and RHL have the same function of calculation, then they usually end up the same. It's kind of like the same here, but we can't generalize again. So let's anyway solve for it. The left hand derivative is the limit as h approaches 0, f of 0. Yes, we need to check the differentiability of this function at x is equal to 0. You might have guessed that by the breaking up at x is equal to 0. So yeah, f of 0 minus f of 0 minus h all over h, the limit as h approaches 0 of f of 0 is just 0 minus 0 minus h. We need to substitute 0 minus h over here instead of x. 0 minus h the whole square times the sine of 1 over 0 minus h all over h, the limit as h approaches 0 of 0 minus, so we can ignore the 0. Negative h the whole squared is h squared. Sine of negative 1 by h by h. And now if you know, the sine of a negative angle is the negative sine, so the negative and this negative is going to cancel out when right sine is negative sine. So in the end you have h squared times the sine of 1 by h all over h. So the limit as h approaches 0 of the sine of 1 by h all over, this is cancelling out, with an h on top. You can write this as 1 by h. Anyway, this h can go on top and have the product as before. Now if you want, you can do a substitution of limits. You can substitution of variables, sorry. So you can let t equal 1 by h. When h goes to 0, t is going to infinity. So now our question is the limit as t goes to infinity of sine of t all over t. Now we had an identity when t went to 0, but now t is going to infinity. So I have a method up my sleeve. I'll just explain it to you. So you know that the sine goes from negative 1 to positive 1, right? Let's just divide everything by x. And now we take the limit as x goes to infinity. So when x becomes really large, this thing will become 0. This thing will become 0. And since sine of x by x is between the two zeros, is greater than or equal to this 0 and greater than or equal to this 0, this thing will also tend to 0. You call this the sandwich theorem or the squeeze theorem. So yeah, so this thing will go to 0. So left hand derivative we calculated to be 0. Okay, time for the right hand derivative. So RHD is equal to the limit as h approaches 0, f of 0 plus h minus f of 0 all over h. Let's use the function definition now. 0 plus h the whole squared times the sine of 1 by 0 plus h. F of 0 is 0 all over h. So it's the limit as h goes to 0, h squared times the sine of 1 by h all over h. That's gonna be the limit as h goes to 0, sine of 1 over h all over 1 over h. And this, you don't want to do the substitution again, it's fine. We just calculated this is 0. So yeah, even the RHL is 0. Sorry, the RHD is 0. These short forms can be confusing sometimes. Yeah, both of them are equal. So the function is differentiable at x equal to 0. Differentiable, it's a big name, at x is equal to 0. And officially you can write this. You can write, so f dash of 0 is 0, or you can also say df of x over dx at x equals 0 is 0. So this says that when you take a very small change in x, you get a respective change in f of x, right? and basically the ratio of both of them at x is equal to 0 is 0. So that's a fancy way of saying the slope at x is equal to 0 is 0. So the rate at which the function grows with a small change in x is 0 at 0. So I guess it's gonna be, the function is gonna be probably flat at that point. Tangent line at that point is gonna be flat. Now say you have a poor function that is defined as x squared when x is less than or equal to 1 and 1 over x otherwise, and they're telling us to analyze the differentiability at x is equal to 1. Yeah, so let's get to the job, guys. LHD first. So I think I'll just skip the formulas for now. The limit as h approaches 0 of f of 1 is 1 times 1, which is 1 squared basically, minus, well, since less than 1, so 1 minus h is still gonna be 1 minus h the whole squared, because this thing applies even for values less than 1, all over h. You definitely want to open the bracket now. 1 minus 1 plus 2h minus h squared. I skipped some opening the brackets and multiplying by the negative. So if we divide everything by h, because h is not equal to 0, we get 2 minus h, and on substitution we just have 2. So left hand derivative is just 2. Yeah, time for the right hand derivative. That's equal to the limit as h approaches 0, f of 1 plus h. For values greater than 1 we use this now. So we need 1 over 1 plus h minus f of 1, which is just 1 squared, all over h. Yeah, we can totally do some simplifications here. So this is going to be 1 minus h all over h times 1 plus h. This stuff is going to cancel out. You have a minus h on top and an h in the denominator. Leaves you with minus 1 over 1 plus h. Now when you substitute 0 in the denominator, the entire thing becomes a negative 1. So the right hand derivative is a negative 1. And yeah, both of them aren't equal, definitely. So you cannot say that f of 1 exists, f dash of 1 exists. You can't say that. You can't write anything for it. So D and E does not exist. Yeah, that's it. Now I think I should have emphasized more on the fact that when we are finding the slope at a given point, say A, and we take a point which is very slightly greater than or less than, say over here I've taken a point which is slightly greater than A. So A plus H. When we do that, when basically we we can draw a tangent at this point, and the value you obtain as the derivative at a, assuming it exists, is basically the slope of this tangent line at that point. So you can, yeah, totally define a tangent line at that point, and its slope will be equal to the derivative. So f dash of a would be the slope of tangent line passing through a. Because the effect of this point can be neglected when you're looking only at the tangent line, because it's very small. The distance between a and this point is very small, because taking the limit as h approaches 0, right? The best approximation. And then again, not only is this, the rate of change of function at this point, or the slope of of how fast the function is growing at this point, but also the slope of the tangent line. Yeah, so you can say that, say if this were your displacement, say this were your say displacement versus time graph, then the derivative at a given point would be the velocity. So say you found the derivative at a to be, say, 6, so you could totally say that the velocity of a body or a particle at at that at that instant a is 6 meters per second. Yeah, I mean, this is the principle of using a speedometer. They give you the instantaneous speed, because they are taking a very small time interval, uh, where we can assume that the displacement doesn't change much. You can assume that the displacement will remain linear. You take two time intervals with a gap so small. So it's delta x by delta t, where the limit as delta t goes to 0. That's your velocity basically, roughly. Yeah. Now, wouldn't it be great that, like every time we have to define a point A, B, or whatever, wouldn't it be great that if we had a function where we input a point, and the output you get is of the derivative at that point. I mean, before we were just taking a point and then getting a solid value. But what if we had a function that did it for us? So you can define the f dash of x, or the derivative function. The derivative function giving the slope of the tangent line at a point x. We can generalize the point because function is general in nature. And of the limit as, say, h tends to 0, x of f of x plus h minus f of x all over h. Yeah, and you can totally, now I've written it for the RHD form. You can also write it for the LHD form. But this is basically the idea of having a derivative function is what actually brings us to the idea of finding the derivative function by the first principle method. Now, instead of getting numerical values such as 2, 3, 5, or integers, now we are going to get a function. So for example, if I were to say, if your f of x is sine of x, The f dash of x is the cosine of x, or written other ways, d over dx of sine of x is equal to cos of x. I'm going to prove this in the next video. We're going to do a lot of them. By the end of the next video, you will be able to find the derivative function of a given function, using this method comfortably. So yeah, we'll only be doing the RHDs because LHD, I mean, I can leave it as an exercise to the viewers, and definitely will, because calculating both, I mean, the technique essentially remains the same, and all the functions that I'll be doing in the next video, they are differentiable at every point. Okay, so yeah, that's it for this video, guys. So stay tuned for the next video. It will be out soon. Please like, share and subscribe this video. Thank you very much for watching. Have a great day.